Hi guys, welcome back to the lesson for today. So we really have been looking at the concept of what it means to have a tangent and what a tangent is all about. Remember that we looked at the first two theorems of a tangent. Now we're going to look at a greater, or rather another theorem, which then talks about a tangent chord theorem, right? But we first gonna investigate exactly what this theorem is all about, and I'm gonna try and move the point for you to see exactly what is it that I'm talking about. But for now, let's just jump right into it. So remember our concept map that actually showed us everything and anything that we were supposed to do. So our investigation is, you can see I have my diagram here, right? And roughly on the diagram that I have, you can see that my angle here and that angle there, they slightly equal, just that off by 0.02 degrees, right? It's because I just used an app, so it's not really drawn to scale, but we will try and see exactly what this means. What is the relationship between the angle measured between the tangent and the chord drawn from the point of contact, right? That's what we are going to try and talk about. Remember, our keywords are a chord and what we call an alternate segment. Now I want to know, what is the relationship between these two angles? Are they really equal, or are they always off like this? That's what we are actually trying to investigate here. Now we need to change the position of D, right? And look at what happens to the size of the angles alpha and beta if I change the position of D. So let me look at that. Changing the position of D, there's really not much that is happening here, but look at my angles there. Do you see? My angles become the same, right? They don't really change. Roughly it's a bit off there, also a bit off, but you can see that they are roughly the same angles that I have there. So that's the relationship between the two. We can really deduce that they are actually equal, though it's a bit slightly off because of maybe the app that I am using here. Now, also, we need to look at the theorem that we are actually talking about here is the angle between the tangent to a circle and the chord drawn from the point of contact, right, from the tangency point, remember that, is equal to the angle in the alternate segment. Going back to this diagram, this is my chord, this is my tangent, that's the chord. The angle in between them will be the angle in the alternate segment. Remember that this is one segment and this is the other segment. Alternate means other. But the condition is that it must be opposite the very same chord that forms an angle between it and the tangent. So if I go back to my diagram, roughly, let me just try and do this. So you see, if I move that point around like this, right, it moves and it no longer becomes the tangency point as I was trying to show you, right? But now if I kind of bring it a bit closer there and to try and show you the point of what we are trying to say here, let me do this. Will it ever get to the same point? Let me try to do that and bring it to maybe the same value so you can see what I'm talking about. Okay, it's roughly the same. The angle between my orange line, which is AC, that's my chord, and between DC, which is the tangent, it must be the same as the angle in the alternate segment, which is angle B, right? I did say that this is gonna be a bit off because of the fact that the app that I'm using, right, is not really allowing me to flourish the way I want to flourish here anyways. But it's roughly still giving us what we want to know in terms of this angle here. So let me just try see. You see, it becomes off with the same value or on with the same value throughout. But you saw that there was a time where it was actually the same. But the big idea here is the theorem is that the angle between the tangent to a circle and the chord is then equal to the angle in the alternate segment. I'm going to show you with my hands. I hope you can follow this, right? This is my chord. This is my tangent. The angle in between here must be the angle opposite this chord on the circumference. I repeat, this is my chord, this is my tangent. The angle here must be the same as the angle opposite this particular chord that I have here with this particular circle. So that's what you please need to note there. So note that, please, because it's really important for you to know that. And our reason will be this is 10-chord theorem. The diagram for you to see would then be, you can see that if I have this as my tangent and using this as a chord, the angle opposite that will be the same as the angle between these two lines, my chord and my tangent. So this angle and that angle, you can see it's opposite that, and the chord forms an angle between those two, right? So that's the important thing there. Now, we need to know how to also prove this, right? So the proof for this is we have a circle passing through point A, B, and C. And then we also have the tangent AP at A. What we are required to prove is that this angle here, BAP, is equals to that angle there, which is C, right? So what does that mean? Firstly, we're going to start with what we call construction. Remember what I said about a formal proof with the first few lessons that we had. With our construction, you're then going to say, draw, let me just erase that, draw a diameter AD, right? And then join DC. Join DC, right? So what am I saying right now? You are going to draw diameter AD, so meaning that's going to be A there, and then you're going to join those. Then I will have this one as, and that is 1 and that is 2, and I will have this as 1 and that as 2. So automatically you can then see, what do I then know here if I want to prove this? Since I said that my AD is a diameter, it means that A1 plus A2 will be equals to 90 degrees, right? And my reason for this will be, remember, radius perpendicular to the tangent. That's what we do know there. Also, I know that my C1 plus my C2 will also be equal to 90 degrees. Why? Because it's angle in semicircle, right? And then what do I know here? I know that C2 and my A1 are actually going to be equal to each other. Why? Because it's angles in the same segment. They are both subtended by that particular arc that I have shaded there. So I will say, but A1, right? My A1 is equals to C2. And this will be angles in the same segment. So automatically, if I have all of this that I've said so far, I can then claim that, therefore, my angle, because I've equated A1 and A2 and C2, angle A2 is equals to angle C1, right? Because already A1 and C2 are equal. And remember, what is my C1 is actually angle C that I said. What is my A2? It's actually angle BAP. And that's what this particular theorem is all about. And then you would have proven the theorem. You don't need to say anything about the converse of anything. No, you would have proven the actual theorem based on that, right? So the main idea here is for us to construct that as well. It introduces those two angles and those two angles, and then I will then talk about this. But this is a formal proof that you really do need to know, because it is one of the proofs that are normally asked from you to actually prove this particular proof that I have here. So that's what tangent chord theorem is all about, guys. Remember that the first two theorems we looked at was a radius is perpendicular to the tangent that are drawn from the same external point, and there's two of them, they are equal to each other. The last one was tangent chord theorem. So for now, let's go to a quick ad break. When we come back, we're then gonna try and put all of this into context and answer a few questions that we need to try and look at together. From me to you, I'm coming back just now. Please stay tuned.